AP Calculus AB, Unit 6, Assignment 16, Office Hours. This is an extra credit review worksheet. One more chance to practice some of the things that will be on your test. So you will be getting some problems. Well, I just give you the graph of the original function. It asks you to identify all these different special points and intervals. So the zeros are just when f of x equals 0. So that those are x-intercepts. So A, C, E, and I. Stationary inflection points are where f double prime changes sign, so it usually starts where it's 0 or undefined. I would emphasize concave down, concave down, concave up, concave down. So a cusp could be an inflection point if the concave changes, but it goes from down to down, so it's not there. F, G it changes, and that's it. Stationary points are where f prime equals 0 only, so those are critical points. So horizontal tangents B, F, and H, just to clarify. So it's going to be F, and H. D is a critical point, and I guess why not? Let's just go ahead and put critical points on here. So critical points would be, just for extra practice, B, F, H, and also D would be a critical point. So intervals of increase of the function. So that's where f prime is positive, so the graph's going up. So A to B, we include endpoints. D to F to H. So D to H should all be one interval. Don't break it up. Intervals of increase of f prime. So that would be the derivative of f prime is positive. So that's the second derivative is positive. So we're looking for concave up, which would be f to g, which we usually wouldn't include the edges, endpoints for concavity, but we're not really looking for concavity. It's just associated with what we're looking for. We want brackets because it said increasing, whereas f prime increasing. Relative extrema. So this is your critical point. This is critical point. F prime equals undefined. F prime equals 0. Here's a critical point, f prime equals 0. Here's a critical point, f prime equals 0. So relative extrema, so we could do relative max would happen at x equals b and h. Relative min happens at x equals d. So relative max min could be a sharp peak or valley. Absolute extrema, so the absolute max happens, happens at, we're looking for x coordinates probably, happens at x equals h, and the absolute min happens at d. But consider the endpoints as possible places. Intervals where f of x is increasing and concave down at the same time, increasing and concave down. So I would say A to B, increasing concave down. I would say D to F, increasing and concave down. I'd say G to H, increasing concave down. Now I need to decide, do we include bracket or parenthesis on the edges? So A is the beginning of concave down, so we can't include it. B is the end of increasing, which we include, and it's in the middle of concave down, so that should be a bracket. D should be a parenthesis because it's the edge of concavity. F is the end of concavity, so it needs to be a parenthesis, even though we include it for increasing, decreasing. G is the beginning of concave down. H is the end of increasing, which we would keep, and it's in the middle of concave down, so we keep it. So there you go. I'm also going to give you pictures of the derivative, of the graph of the derivative. And so we have to find pretty much all the same things from the derivative. First thing I would do is I'd label this graph. F prime is positive, increasing. F prime is negative, decreasing. F prime is positive, increasing. F prime is positive, increasing. This is a critical point, critical point, critical point. This is a relative. It's going up and then down. This is relative max. The graph is going down and then it goes up. Down and then up. It's got to be a valley, relative min. Graph's going up, flattens out, and then goes up more. It's neither relative max or min. Concavity is the derivative of the first derivative. So this is a graph with derivative values already. So the slope of this graph gives you a second derivative. So this is concave down. F double prime is positive, concave up. F double prime is negative, concave down. F double prime is positive, concave up. So I think we probably have about everything that we can think of to answer this question. So relative min is at x equals 3. Inflection point is at x equals 2, 4, and 5. Intervals where f is increasing, well, I'd say 0 to 1, including the endpoints. 3 to 5, 5 to 6, 3 to 6, all 1. Don't break it up. And intervals where f is concave down is 0 to 2, parentheses, and then 4 to 5, parentheses. So there you go. We could try and sketch a graph of what the function would look like that this derivative is of. And so we really just need increasing, decreasing, concave, or down. We have an initial condition, so we're going to start there at 2. First chunk is going up, but concave down. Next chunk is going down and concave down. Next chunk is going down, but concave up. Next chunk is going up, but concave up. Next chunk is going up, but concave down. Next chunk is going up and concave up. So something like that. Okay, find the x-coordinate of all relative extrema. So I've given you the derivative already. Take advantage of it. Do not take a derivative. So we need to set equal to 0 undefined. You should label that. So we get x equal, the critical points are x equals -3, which is going to bounce off the graph. X equals 4. If you set this equal to 0 and you solve for it, you take the natural log of both sides, you get x equals the natural log of 2. Okay, so these are our critical points. So we're going to do a line check, of course. Let's do line checks. Label the line check. Now, natural log of 2, the natural log graph looks like this, right? And that's natural log of 1 is 0. So 2 is definitely positive. Is it bigger than 4 or less than 4? Well, natural log is asking you, what do you raise e to get 2? And e itself is 2.71. So it's going to be less than, okay, let's think about this for a second. Log base e, what do you raise e to get 2? If you raise it to 1, it'd be too much. I feel like it has to be, so you're asking, what do you raise e to get 2? What's 2.71 raised to get 2? I feel like it has to be less than 1. Well, it's for sure smaller than 4. Okay. So we have a -3, and then the natural log of 2, and then 4. I'm going to test a value. X equals 5, positive, 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 everything's positive. Right? Watch out for this guy. Positive, negative, positive, positive. So I like draw little arrows on these. So this is increasing, increasing, decreasing, increasing. This is a relative max. This is a relative min. So lots of good stuff. So the relative max is at, I'm just trying to find the x-coordinates, at x equals natural log of 2. And the relative min is at x equals 4. I'm getting thrown off there. Natural log of 2 on the calculator. Let's see. We can do it real quick. natural log of 2. Okay, the thing I was confused, I was thinking it had to be bigger than 1. So it's definitely, it's got to be something between 0 and 1. You know what I mean? That's what this natural log of 2 is. Because 1 would give you e, and natural log of 1 would give you 0. So it's somewhere between 1 and, or 0 and 1. Okay, there you go. Make sure you label your graphs. I'm going to take off points for people who don't label their line checks, that don't show me what their test is. Show your work. Okay, next one. You can do more function analysis with the original function. So lots of line checks. Where is the graph above the x-axis? So we're looking for where the function is positive. So this isn't, I don't actually do this that much, but you would just start with the original function and factor it, smallest exponent. That would give you x to the 3/3 minus 10 equals 0 undefined. So that's going to be first. So x equals 10 and x equals 0 are zeros, not critical point zeros. And let's see, this one is going to get repeated. So if we do a line check on the original graph, 0, 10, repeated, test a value, x equals 11, positive, negative, negative, so it's below the x-axis, above the x-axis. And we want to know what it was above, so it's there. It's from 0 to positive infinity. You should not include the endpoints on that. Okay, so that's that. Does this have any domain issues? Any negative exponents that would cause undefined? Nope. Any denominators in the rational exponents that are even numbers that would give you even roots that can't be taken as negatives? Nope. I think we're good on here for domain, but I do want to come back to domain and talk about some things. I will after this problem's done. So decreasing is where f prime of x is negative, f prime. So we got to find f prime, and that's going to be 5/3 x to the 2/3 minus 20/3 x to the negative 1/3 set equal to 0 undefined. We want to factor this. Label your work, please. We're going to take a 5/3 out and x to the negative 1/3, smallest exponent. When you divide x to the 2/3 by x to the negative 1/3, rules of exponents from algebra 1 say to subtract the negative 1/3 from the 2/3, which is going to add it, and you're going to add x to the 3/3 minus 4, which is x to the first. So x equals 0 and x equals 4 are critical points. We're going to do a line check. And 0, 4, test a point, x equals 5, positive, negative, positive, arrow up, arrow down, arrow up, increasing, decreasing, increasing, relative min, relative max. So you can find a lot of answers on this. We are specifically looking for where it was decreasing, so that would be 0 to 4 brackets. 0 to 4 brackets. Concave up is where the second derivative is positive, so we need to find the second derivative and take the derivative of the first derivative. So that's going to be 10/9 x to the negative 1/3 plus 20/9 x to the negative 4/3. I'm going to set it equal to 0 undefined. We're going to factor it. We're going to take a 10/9 out and an x to the negative 4/3, smallest exponent. When you divide that out, you're going to get x to the positive 3/3 here, plus 2. So that's going to be a 1. So x equals 0 and x equals negative 2 are potential inflection points. This one, because of the even numerator in the rational function, is repeated root 4 times, so that one's not going to be an inflection point. This one will be an inflection point. We're going to do a line check, -2, 0, test a point, x equals 1. It's going to all be positive, stays positive, negative, concave down, concave up, concave up. That's an inflection point. This is not an inflection point. But you're going to have to break it up. So concave up, you got to do -2 to 0, and then 0 to positive infinity. We don't include the endpoints. Concavity is not defined at x equals 0, so you can't say it's concave up. Now, part D says to make a sketch and identify all these special things. So we've already kind of found everything. So if we're doing a sketch, just a quick sketch, we have zeros at 0 and 10. So I think we'll start with putting the x-intercepts on the graph. And then on the next one, we have a relative max at 0, but the derivative is undefined there. So it's not a smooth one, it's kind of a sharp one, kind of like a cusp or something. In fact, from 0 to -2, it's concave down, and then -2 to 0 is concave up. So it's going to be concave down and then concave up. And then it's concave up from 0 onwards. There is at 4, there's a relative min, but it's going to be a smooth graph. It's decreasing and then it goes up. Decreasing from 0 to 4, it's going down, and then it goes up from 4 on, and it's concave up the whole time. So something like that. This is your relative max. This is your relative min. This is going from concave up to concave up. This is an inflection point. This is a 0. This is a 0. This is also a critical point. This is a critical point. It's a stationary point, has a slope of 0. So absolute max doesn't really have one because it keeps going up forever. Absolute min doesn't have one because it keeps going down forever. So I think that's pretty good. Now I want to revisit the whole domain thing real quick. Let's talk about domain. And this is, we already checked the domain of this problem, but I want to add some notes about domain. Okay, I want to go over some basic problems. So if you'd originally been given a problem like this, x to the negative 1/3 plus 3 to the 3/2, there's some issues here. X can't be 0 because of the negative. Okay, so that better not show up in any of your answers. The fact that this has a even root, this is the same thing as the square root of x cubed, and square roots, the inside has to be greater than or equal to 0. So this is going to give you another issue with your domain. Okay, so watch out for that. Now, just because on the derivatives things show up as being undefined or whatever, that doesn't matter. It's the original function that you got to worry about. Okay, now so anyways, yeah, just keep an eye on the domain. Okay, number 6, on what intervals is f decreasing? Got a little trig, of course. Trig never dies, trig never goes away. Decreasing, so we got to take the derivative, and that gives you cosine of 2x, and then times the derivative of what's inside. Chain rule is 2 plus derivative of x is 1. We're going to set it equal to 0 or undefined. So then we got to do a little solving trig, which is -1 divided by 2. Alpha equals, cosine starts at 1, root 3 of 2, root 2 of 2, 1/2. So it's further angle 0, pi over 6, pi over 4, pi over 3. Quadrants 2 and 3 is where it's negative. So 2x equals, quadrant 2 would be 2 pi over 3 plus 2 pi k. And quadrant 3 would be 2x equals 4 pi over 3 plus 2 pi k. And then we divide by 2. And we get x equals pi over 3 plus pi k. And x equals 2 pi over 3 plus pi k. Now we only want the critical points between 0 and pi, so we're going to go with pi over 3 and 2 pi over 3 for critical points. So then we would do a line check, f prime of x. Now let's go back up here. Any domain issues? What's the domain of that? All reals, negative infinity, positive infinity. You plug anything you want in the sign and whatever, no problems. Okay, line check. Pi over 3, 2 pi over 3, 0 to pi. Be careful, there's only pi this time. Test a value. I'm going to test 0 in the derivative. Make sure you test in the derivative, which is going to be positive, negative, positive. So it's increasing, decreasing, increasing, increasing, decreasing, increasing. Relative min, if you're looking for that. Relative max, if you're looking for that. Now, we just want a decreasing. So the answer is just going to be pi over 3 to 2 pi over 3 in brackets, because we include the endpoints for increasing, decreasing. So there you go. Number 7. This is generally a domain issue problem, right? So what's the domain of this? When you go and do work about it, show me and convince me. So x squared plus 2 is got to be greater than 0. Now, if you wanted to solve this, this would give you x equals plus or minus I root 2, okay? Which won't show up on a line check. So there's nothing on a line check. You can test any point you want, like x equals 0. It's going to be positive no matter what, or true no matter what. So the domain is all real values. So you got lucky this time, okay? But I'm looking for it, especially on a problem like this. Natural logs always have domain issues, right? So concave up, we got to take the first derivative, and that's going to be 1 over what's inside times derivative of what's inside. Okay, and then we take the second derivative. It's going to be low d high minus high d low all over low squared. It's going to be 2x squared plus 4 minus 4x squared. Leave the denominator factor. So f double prime of x equals negative 2x squared plus 4 over x squared plus 2 squared. So let's try and factor this. Factor out a negative 2. So x squared minus 2. And then that's going to be negative 2, x plus the square root of 2, x minus the square root of 2. Now the one on the bottom is going to give you x equals plus or minus I root 2. So we're not going to use those. You're going to set this equals 0 and define. That should be in your work. And from there we get x equals negative root 2 and positive root 2. These are our inflection points, and they are for sure inflection points because they're not repeated. We do a line check to figure out where it's concave up or down. So negative root 2 to positive root 2. Test a point. I'm going to test 0, I think, in the derivative, in the second derivative. So that's going to be positive 4. It's going to be positive. Positive, negative, negative. Concave down, concave up, concave down. Which means this is an inflection point and this is an inflection point. The answer is, where is it concave up? So that's just this part right here, negative root 2 to positive root 2, parentheses, is where it's concave up. So try another one. Okay, find the x-coordinates of all relative extrema. What's the domain of this guy? This is the same thing as x over e to 3x. Can we get division by 0? Because that would be bad. Nope, nope. Domain's a negative infinity, positive infinity. So I'm probably going to look for some kind of comment on these problems. Okay, relative extrema. So we got to take the derivative. And so there's a product rule here. X times derivative e to the negative 3x is e to the negative 3x times derivative what's inside is negative 3 plus e to the negative 3x times the derivative of x is 1. We're going to set this equal to 0 undefined. I'm going to go ahead and start factoring right now. We could take an x e to the negative 3x out. So then you have negative 3x plus 1 left over. So x equals positive 1/3, and that doesn't do anything. That's your single critical point. We're going to do a line check. Okay, undefined would come from that because it's in the denominator, but it doesn't give you any values. Test a value, x equals 1. It's going to be negative, positive. So increasing, decreasing, relative max. Right? So now to say relative max value, just location. So the relative max is at x equals 1/3. The relative min is none. It doesn't have one. Now, just as a side note, what if I asked you for the absolute max location? Well, the absolute max would be at the relative max, right? That is the absolute max. And the absolute max value would equal the original function with 1/3 plugged into it. So this is the absolute max at x equals 1/3. Not through extreme value theorem. There is no absolute min. This graph goes down forever. Okay, let's find the derivatives. Now, I think we're just going to use, I would use some log rules here and break this up. Unless you really like making the work harder for yourself, this will make it easier. And then we take the derivative implicitly. Derivative e to the 2x is e to 2x times derivative of what's inside is 2. Plus the derivative e to the y is e to the y, but then the derivative of y with respect to x is dy dx. Derivative natural log of x is 1 over x plus 2 over y. Don't forget dy dx. So that's the derivative. Now we got to get dy dx by itself. So let's see. We can move them on the same side, dy dx. Factor out the e to the y and the minus 2 over y. Move the other stuff to the other side. Divide by e to the y minus 2 over y. I don't want fractions and fractions with negative exponents. We need to multiply top and bottom by xy. So this is going to be y minus 2xy e to the 2x over xy e to the y minus 2x. Now you could do the problem the way it was originally written if you really want. It'd be e to the 2x times derivative of what's inside 2 plus e to the y times derivative of what's inside is dy dx. And then over here you do 1 over what's inside times the derivative of what's inside. And you better put parentheses around this. This is product rule. X times derivative of y squared is 2y to the first, dy dx, plus y squared times derivative of x is 1. Now, eventually, this should give you the same answer. Okay, this will give you the same answer. I would probably go ahead and distribute this. So you get 2e to the 2x plus e to the y dy dx equals the x's cancel, one of the y's cancel, so you get what, 2 over y dy dx plus 1 over x. So you want to get your dy dx's together on the same side. So e to the y minus 2 over y equals 1 over x minus 2e to the 2x. Divide both sides by e to the y minus 2 over y. Should be looking familiar. Don't want fractions and fractions. The trick is multiply by the least common denominator. And we get y minus 2x y e to the 2x over xy e to the y minus 2x. Hey, what do you know? It's the same answer. Two different ways. Your choice. Log rules, though, I think are kind of nice. Okay, inverse functions and their derivatives. So this is the whole new school thing. Find the equation of the tangent line. Okay, to the inverse at x equals 3. So what I'm going to start with is that x equals 3 is on the inverse function. I like writing this stuff out. It helps me keep things straight because that's the hardest part of this problem. The derivative is easy. Plugging a number in is easy. Flipping is easy. Getting the right numbers to plug in is the hardest part. If x equals 3 on the inverse, then y equals 3 on the original function. And if we know the y value on the original function, we can plug it in and find the x values that create it. So I'm going to do that. Now, we're getting two answers here, but we specifically, well, it doesn't really say. Usually it's the right half or the left half. I'm going to just assume it's the right half. Or, let's just add some directions here. Let's say x is less than 0. So that means we'd go for the negative one. Like they tell you that at the beginning. Okay? X is less than or equal to 0. That's your domain. That goes with that function. So we have the x value. That's going to be the y value in the other. So we're going to take the derivative of the original function, which is super easy, 2x minus 2. We're going to plug negative 1 into it because x equals negative 1 in the original corresponds to x equals 3 in the inverse. And then the derivative of the inverse at the corresponding x value, 3, its slope is just going to be that slope flipped upside down. Not negative reciprocal, just reciprocal. Now I guess I'm not done. That's the function. We're trying to write the equation line, so we need an xy pair. We have x equals 3. We need the y that goes with that. Well, the x equals negative 1 on the original function. That means that y equals negative 1 on the inverse. So our point is going to be 3, negative 1. And the equation of line is going to be y plus 1 equals negative 1/4 x minus 3. I would just leave it in points so far. Unless you like doing extra work, that might cost you points that you already earned. Let's do this one. Find the equation of the tangent line for this graph. Now, this one seems like the same. That is related to inverse and stuff, but this is a very specific inverse function that's already been given to you. So there's two things. We need the point, so we're going to plug negative 1 in. And what we're trying to do is we're trying to say, well, tangent of what equals 1? But I always think of tangent as sine over cosine. And so then I want to think as fraction. Then I got to think, well, what fraction, what angle would you plug a sine and cosine that would eventually give you 1 over 1 and 1? Well, that would be root 2 over 2, root 2 over 2. That'd be alpha equals pi over 4. That'd be quadrant 1 and quadrant 3. Quadrant 1 where they're both positive, quadrant 3 where they're both negative. That would give you a positive result. But we are looking for principal values, which has to be quadrant 1. So that's going to be pi over 4. So y negative 1 equals pi over 4, which means our point for our tangent line is negative 1 pi over 4. So we got half of what we need. We need the derivative. Now remember, the derivative of inverse tangent is 1 over what's inside squared plus 1. But this time, there's something more complicated. So like maybe using the chain rule version might maybe help you feel better about it. Like whatever's inside the function is what gets squared down here. So the derivative in general is going to be 1 over x to the 6th squared plus 1 times the derivative of what's inside 6x to the 5th. So that's the derivative. Then we want to plug negative 1 into it. So it's going to be 6 times negative 1 to the 5th power, or negative 1 to the 6th power, squared plus 1. So it's going to be negative 6 over 2 is negative 3. So that's your slope. So the equation of your tangent line is going to be y minus pi over 4 equals negative 3 times x plus 1. And I would just leave it in point slope form. Don't do extra work. All right. A lot of good stuff. Okay, one last related rates problem. Good times, a cone problem. Feels like a cone could be a very realistic option, but container has the shape of an open white circular cone as shown in the figure above. The height of the container is 10 centimeters, and the diameter of the openings is 10 centimeters, which means the radius would be 5, right? And we get a little right triangle here and a right triangle here, so we have similar triangles. Water in the container is evaporating, so because it's going out the top, I'm drawing an arrow, so that the depth h is changing at a constant rate of negative 3/10 centimeters per hour. The volume of a cone with the height h radius r is given by v equals 1/3 pi r squared h. So what are they telling us? So we know the volume equals 1/3 pi r squared h. What's that rate they give us? They said water in the container is evaporating so that its depth h is changing dh dt at a constant rate of negative 3/10 centimeters per hour. Now, they gave us the negative this time, which is really rare because we should think it's negative because the radius should be dropping as water evaporates out. But they were nice and gave us a negative. They usually don't do that. So, A says find the volume of the water in the container when h equals 5. Indicate the units and measure. Make sure you always put the units. Now, I think we need to use similar triangles here. And so it's going to be r over h equals 5 over 10. And they're talking about h, and dh, dt. So I think we want to get all h's. So r equals 1/2 h. I'm going to plug that in for r to get our volume equation in terms of all h's. So that's going to be pi over 12h cubed. That's the volume formula we want to use. Okay. Now it says find the volume of the water when h equals 5. Well, that's perfect. We'll take advantage of that right away. So if h is 5 cubed, it's going to be 125 pi over 12. What are the units? It's volume. So it should be a length cubed. Right? B says find the rate change of the volume of the water. So we're looking for dv dt with respect to time when h equals 5 and indicate units of measure. Okay, so we got to take the derivative of our new volume formula with all h's. dv dt equals 3 pi over 12 h squared dh dt. They gave us dh dt, so hopefully we use it at some point. H is 5, right? And then this should be pretty straightforward to find dv dt. So we got pi over 4, we got 5 squared, we got negative 3/10, and we should expect the volume to be negative, the rate change. We could take one of these 5s out. So negative 15 pi over 8. The units should be volume, which is cubic centimeters, over time, which is, if you look in here, hours. So that's dV dt. C says, show that the rate of change of the volume of the water, that'd be dV dt, due to evaporation, is directly proportional. Directly proportional. And that's when you just multiply by some constant. And K is a common letter to use for the constant of proportionality. Directly proportional to the exposed surface area of the water. What is the constant of proportionality? So we're trying to show that this is true. Now, when they say surface area, they mean the literal surface area of the water, not the kind of general geometric area around a whole shape, just the top area that's exposed. So I think to get this, by the way, surface area would be pi r squared. We probably want to get something where it's a number times pi r squared. So the fact that we want r, I think means it might be helpful to get our equation in purely r instead of purely h. So if r equals 1/2 h equals 2r. So I'm going to rewrite my volume formula. Volume equals 1/3 pi r squared, and replace the h with the 2r. So it's going to be 2 pi over 3 r cubed. So I think that might help. So then I'm going to take the derivative, dv dt, and I'm going to get 2 pi, the 3 is going to cancel 3, r squared, dr dt. Now you might notice, look, we've got a pi r squared, so that's good news. We need to figure out what dr dt is. So if r equals 1/2 h, then we could do another little mini related rates problem here. dr dt equals 1/2 dh dt. And we already know that dh dt is negative 3/10, which makes dr dt negative 3/20. So that's what we're going to plug in right there. So 2 pi r squared negative 3/20. And then I'm going to simplify it. And 2 goes in that 10 times. So it's going to be negative 3/10 pi r squared. Now, by the way, we've confirmed that it is directly proportional to the surface area of the water. The constant of proportionality is this value. So we could say the constant of proportionality is negative 3/10. So there you go. That's it. Whatever you think you need extra practice on, there's plenty of worksheets that you've done already. Print out a clean one and just do the problems that you know you need extra practice on. Related rates, whatever it is. Line checks, whatever it is. Graphs of the derivative. New derivative rules. Make sure you're ready.